start.
I was calling Matzi. This is a linear combination of everything Matzi likes.
Why?
Complexity, TTbar.
The title.
Yeah, the title.
Okay, good. Well, if you are ready, it's a pleasure to have Sergio Aguilar Gutierrez, now in Leuven, but as he's saying, he's going to Okinawa soon. So he's going to be talking about moving boundaries with the double scale SYK model. Please, Sergio.
Okay, thanks a lot to the organizer for giving me the opportunity to speak, and this is a privilege and an honor to be able to give this talk about an upcoming work that has been being made possible thanks to collaborate with other people. Okay, so the motivation for this work is about developing the holographic correspondence outside the ADS-CFT type of examples that we know about, and there are different approaches to this type of equations, and one of them is with these so-called TTbar-deformations that can either allow us to change the local geometry with the so-called single trace deformations, or there is also the possibility of only changing the asymptotic boundary conditions, that is with the double trace deformations. And something exciting in this type of a direction is also that the lower dimensions offers like a new possibilities in order to make like explicit examples of the correspondence outside the ADS-CFT type of a regime. In examples where we have actual analytic control, and the particular model that I'll describe about is the double scale SYK model that has motivated several proposals of non-ADS holography. And one question we would like to address is how to distinguish among them. So this is the only for the talk. I'll introduce the double scale SYK model, what's the particular boundary dual theory that I'll describe about, and give you some reasons why this is like the best developed type of description. And I'll tell you about this stretch horizon type of a conjecture of the Susskind that also motivate this work. About the T-square deformations that basically allows us to locate the double scale SYK model at certain locations in the Paul dual that will be important. About the flow equation of the energy levels, and I'll describe about the semi-classical thermodynamics. So there are several things that I'll have to skip given the time constraints. So the double scale SYK model is let's start just with the SYK model. So consider a system with fermions, and that has P all-to-all interactions, and that the couplings of this type of a theory are given by some Gaussian distribution. There are other type of distributions you can choose, but for describing the system in an ensemble average way, then this is the one that has been best developed so far. So the so-called double scaling limit, you basically take the number of fermions and the all-to-all interactions to infinity, but you keep certain ratio between them to be fixed. And given this limit, you can have a statistical description of the system when you study quantities like ensemble average moments of the Hamiltonian. There are other interesting observables that I will not have time to discuss. This is the particular ones that we care about for the moment. So these are this is when you take this ensemble average of the Hamiltonian, you take a trace with certain powers, and this is what you call the Hamiltonian moments. So you basically express them in terms of a trace over these strings of p number of fermions, and basically the using this double scaling limit, then there's a nice picture where you actually can map the system into a representation where you take that this trace is basically given by this circle, and where the insertion of these strings of fermions is given by each of these vertices, basically given the Gaussianity of the distribution of the couplings. This implies that there will be only like a Weak contraction between pairs of these strings of fermions, and these Weak contractions are basically what we call the chords in this type of a diagram. So the counting problem of the original system basically reduces to a simpler one where you only care about the number of intersections between the different type of moments or different Hamiltonian intersections in the system. So the ensemble average theory then can be described by a type of auxiliary Hilbert space, where you basically cut the diagram at any given location between this pair of fermionic vertices, where you have the strings of fermions, and here you basically count the number of open chords, basically discrete with contractions. And with that, you can try to describe the system with this auxiliary Hilbert space using the discounting parameter. And then the moments of the Hamiltonian that can be used in order to study the partition function of the system can now be described in terms of this quantity that only depends on. Basically, when you have this thermal circle where you start with 0 open chords and you end up also with 0 open chords. The Hamiltonian of this auxiliary system acts on this basis in this type of way. There are other like orthogonal transformations that you can use if you want a different basis, but this is the one that we will care about in this talk. And basically, you can also find the eigenvalues and eigenvectors of this system because there is a recursive relation. This is basically related to this so-called Q-deformed, Q-Hermite polynomial. And because the system is like an ensemble inverse one, then the energy spectrum is continuous. Why should we care about the double scalable model? First, it has finite entropy and finite energy. The partition function is finite even at infinite temperatures. So by definition, this is like something that is UV complete. And another motivation is that you have like the low energy regime of this type of system. It describes JT gravity. Also, the 2 and 4-point functions have been exactly solved at all energies, and they're like general rules for all amplitudes, basically by this group, mostly based on Israel. And there are several proposals for non-ADS holography that has been like catalyzed thanks to this development in the double scale model, the SYK model, by several authors. We will focus on a particular one. I'll tell you about why this is like a most reasonable type of description. And there's also some very nice mathematical structure behind this about the quantum groups SYK2 for this type of system, connections with the Leuven gravity, inverse-orthotic QFTs, and it also has a type 2-1 point element algebra that people care about, for instance, in the CT space. There is this so-called stretch horizon conjecture of such kind. There are like 4 conjectures in the original paper. I'll just try to go to the other results. But the first one tells you that the fundamental degrees of freedom for the CTR2 space are like hyperfast scramblers that scramble. Well, in fact, is thought to be more general than the 2 dimensions, but they are thought to be hyperfast scramblers in the sense of OTOCs, where you have the scrambling time as a notion where you have like an exponential type of decay for the out time order correlators. And where this time scale of the scrambling, where you have like basically this dissipation of information, is of the order of the CT horizon. So this is like an order 1 type of parameter of the scrambling time. Meanwhile, if you have like an n-body system, then you expect that you have something that scales like order n. That will be a very long time for this type of double scaling cases where you would like to study these systems. And basically, this tells you that it's something that happens at a very fast rate. The other part of the conjecture is that at the zero temperature limit of the double scale SYK model describes the CT space. So this is like a very concrete type of proposal for non-ADS holography. But recently, it has been shown by this group using canonical quantization methods that basically you can exactly match the Hamiltonian of the auxiliary system of the double scale model from a sign dilaton type of theory, dilaton theory with a sign potential. So the question for us is, okay, how to reconcile these 2 pictures, and whether when you locate the double scale model at a stretch horizon in the holographic dual, can we recover similar thermodynamic properties to those of the CT space? We also studied like the quantum information ones, but we will not go into those. Okay, so this is the okay, and perhaps something that I should mention is that this stretch horizon in the CT space is basically this surface that is like very close to the cosmological horizon. is basically the most natural location where you can have like a notion of a boundary for the theory. Although you have a closed universe, and then you really don't have the boundaries. But this is just a most natural location to put the holographic theory dual. Okay, so the explicit theoretic dual for this sin dilaton-gravity theory is basically given by this type of geometry. You have this as the blackening factor. You can see that they're like at the degeneracy of the horizons where this goes to zero, and then you have like different saddle points that you should in principle account in the path integral computing the different quantities. So there are these so-called generalized Brown-Henoux boundary conditions, where you is basically the Euclid boundary condition where you also put that these parameters of the metric and the dilaton can be complex. So this is a drastic departure compared to the zeta space where you have a real geometry. So there are like some conditions in order to match like the different parameters between the ones in the bulk and the ones of the double SYK model. Then there is these matching conditions that you can impose with the energy spectrum, and also with the thermodynamic temperature. Something important for us is that there is nearly the zeta2 type of geometry that arises when you are studying this model. Basically, it has like this cosine Ricci scalar just follow from using the metric that I gave you, and then you can see that there will be some regions where you have a positive Ricci curvature, and it can be nearly constant if you pick that this R is nearly constant. But important for us is basically that if you fine tune this parameter that basically relates to the location of the black hole horizon, then the location between two horizons can be basically positive, and then you have an approximate notion of the zeta2 if you in particular teams of this model. And then the point about our work is basically to isolate these positive curvature regions because we have like a complex geometry in principle, and we would like to study the properties of these locations where you have an approximate description of the zeta space and where that agrees with the conjecture of Susskind. Okay, so I'll introduce these TTbar-deformations and developed by Hartman and other people, but now applied to one dimension. So this is like a d-dimensional generalization of TTbar, but basically now is only with this description where you have, except in the one-dimensional case, with the description where you have like a finite cutoff in the bulk theory dual. And that's basically the input that you put in when you try to make the derivation about the flow equation controlling the energy levels of the deformed system. So we consider this as a general dilaton-gravity theory. This is because I also study like other proposals, not just the Sin Phi that I'll be mostly focused in this talk. And then this is basically how you introduce the action. There is a condition for in order to obtain like a finite action for general potential phi. And basically we use this Hamilton-Jacobi equation that tells you about the location of the radial coordinate of the boundary that is now at a finite location. So basically you're putting like a finite cutoff using this Hamilton-Jacobi equation, and then you basically try to map what's happening in the bulk to what's happening in the dual theory. This is the particular Hamiltonian constraint that one has for general dilaton-gravity theories, and it is given in terms of this canonical momenta. So I will not go into details because of the time, but basically you record a same type of a looking flow equation, basically describing the energy levels. And this basically follows because in one dimensions, the stress tensor is just given by the energy spectrum of the boundary theory. Something nice about this is that this eta parameter that appears in the so-called TTbar plus lambda 2 deformations also appears like very naturally when you do this whole procedure. We will be mostly focused on the case eta equal to 1. This is when you have like the case I told you about that you need for relating this parameter of the potential and this this term appearing in the quantitative of the on-shell action. This is when you have the on-shell action is finite. When you basically start with the theory at the asymptotic boundary and you move it somewhere in the bulk. So for In this case, the energy spectrum is described by this condition, and basically there are like two possible signs. The one with the minus is connected to the acid solution, and the one with the relative plus is connected to a non-perturbative solution. They both describe different physics, and because of the time, I will only talk about the negative relative sign. Okay, so the point about our work is under what conditions can we recover a real energy spectrum, because now the metrics are complex, and then this parameter y will be in principle complex, and related to that is that the metric is also complex, so there is really not like a real time evolution generically, but there are some cases where you can recover it, and those are basically given by doing contour deformations in the complex plane of R. And basically, you put the boundary theory that started at some location and in this complex plane, and now you put them somewhere along the real line, and basically at these locations you recover the energy spectrum. So there are two conditions or two possibilities, and they describe like the different type of configurations. Basically, when you put the boundaries that are like very close to the cosmological to the black hole horizon at r equal to theta, and to this r equal to minus theta, there is another horizon. Or there is this other possibility where you put them at this boundary location at very close to this r equal to theta or r equal to 2 pi minus theta. So these are like two interesting limits where you can record that this light blue region describes this positive curvature region, and this the rest is basically the negative Ricci curvature region that is not as interesting, but for the purposes of computing the thermodynamics, this is also something that works. This other one is more useful when you compute correlators, but we will not describe that because of the time. So there's a semi-classical regime that basically you can record that the on-shell action takes this form. There is like a 1 over log Q, and basically because of the 1 over log Q, you can do the evaluation by path integral methods with a saddle point approximation that they works fine. And that's basically what we mean by this semi-classical type of approximation. This is like how you can treat for computing the energy levels of the deformed theory, and also the spectrum. And there is a microcanonical temperature that appears. So these are the results for the deformed energy spectrum. Basically, you see that when you put this stretch horizon parameter that I'll try to recall you how I describe it, that is with this boundary location. Then you record that when you're like very close to the black hole horizon, basically this gives you that very similar to the stretch horizon conjecture, that the energies and other quantities basically grow to a very fast rate respect to they basically become localized respect to the zero temperature case. And you record exactly the same for this thermodynamic temperature. And something nice to compute is also this so-called heat capacity. This is something that tells you about the thermodynamic stability of the system. You see that exactly as in the Sitter-2 space, the heat capacity becomes negative when you're like very close to, in this case, to the black hole horizon, or there's also a cosmological horizon that I didn't describe. This is with the Dirichlet boundary conditions inside the static patch of the Sitter space. You record exactly something very similar, that the energy becomes like a very mostly localized to zero temperatures when you're at this stretch horizon regime, and something also very similar to the thermodynamic entropy and for the thermodynamic heat capacity. And it becomes negative because of the instabilities in the DS space. These are other topics that I didn't have time to discuss, and I'll just go to the summary. So we introduce a novel type of T-square deformations. Other approaches always assume that they just start with some type of ADS-CST holographic dictionary, and then you push the boundaries. But here we're starting directly with a non-ADS holographic theory. We introduce a novel protocol in order to probe these positive curvature regions in the nearly the Sitter-2 description of the Paul dual to the double SYK model. And basically, we found that there is an hyperfast growth of thermodynamic quantities, very similar to the ones that have been conjectured by Susskind. There is also a quantum information type of approaches, or also for correlators that I did not have time to discuss, but exactly that's what's happening in those cases as well. So briefly, the outlook. So something very interesting that also happens is that when you introduce an end of the work brain in the sense of this previous work in the double scale SYK model, then you require like a very similar or very complementary thermodynamic properties instead of like modifying the energy levels by a parameter given by the tension of the end of the work brain. Then you modify basically the thermodynamic entropy, and that also modifies the quasi-local thermodynamics of the system. And there are other points that I will not have time to discuss, but you can ask me about. So thank you a lot for the attention.
Thank you very much, Sergio, for your talk. So it's perfect in time.
Okay.
So, well, we have time for a few questions.
You can ask anyone.
Yeah, Mattia has.
Yeah, Sergio. So I have a lot of silly question maybe.
Sure.
When you put the potential, you put a sign, right? So this scalar is compact. So you should care about topological corrections to this maybe, right?
Yeah, exactly. So that's an important point, but yeah, so this is why we have this expansion parameter in the for instance in JT-gravity and also in other theories of dilaton-gravity theories where you also put some constraints on the theory. Yeah, basically this finite parameter that you put in the theory. Basically, you have to impose that this finite is like a very large parameter compared to the scale of this dilaton. And in that case, then this topology is the one that dominates the path integrals if you're studying that type of cases. So in that case, you can basically only care about this topology in that case. But yeah, absolutely, you should also care about the higher genus type of topologies if you want to like do a very precise I don't know description of this Sin Phi dilaton theory.
Also, when you were describing this as a dual of the zeta2, were you talked about like having two static patch, right? No, not only one. You are looking at two static patch. So this is like in the Euclidean, like a two different spheres.
Yeah, it's a bit more complicated than that, I will say, because yeah, it depends on what exactly. Because this is not just the zeta2. In principle, you have uh, as I was describing, perhaps in this relation, that now the Ricci curvature takes this form. So and now in principle you are like in a complex plane so it can be something very, very complicated. It can be also a cosh or something different. So yeah, in principle, then the global geometry is not the zeta2. They are like only some subregions of the geometry that approximate to the zeta space, and only in like a very fine-tuned situations where you basically what I was describing at the start, I think. Let me put this here. Just sorry, maybe I lost where I have it in the slides, but basically you need to tune the location of this parameter theta to be very close to pi. In that case, basically you record that the location between the consecutive horizons is very approximately to be the one of a constant and positive Ricci curvature, where you have like a nearly the zeta2 physics.
And you can see somewhere the Schwarzschild mode or something like that.
Yeah, that's a very, very interesting question, but yeah, it's more complicated. So this is still in development. There is a Q-Schwarzschild formulation of this in terms of the Euclidean path integral, but to make it as more similar to the analogy in JT-gravity, where you can actually recover it from the on-chill action evaluated for the boundary on-chill action, then that's something that is still in progress.
Okay, thank you.
Alejandro.
Alejandro, yeah.
Just this is probably related to a previous question by Matthias, but let me ask it, just vague terms. So the entropy that you described there, which goes like the free energy that you described there, goes like 1/tau.
Okay.
So this is dual. This is like the growth. So it gives the charge which is dual to a chemical potential. it means that you have energy density going like square root of that charge. So, and you're measuring entropy, you're counting states at that level of charge, let's say. But in the zeta2, there is no charge. The zeta2, it doesn't have any charge on that. So what is, seems a bit like a contradiction. What is the
Yeah,
explanation?
it's a very confusing topic that also has some discussion between the argument of Susskind that basically saying that you should count the entropy of the zeta space as something that goes growing with the number of degrees of freedom, but meanwhile in this other type of approaches where you have like an ensemble average theory, then the parameter that is controlling like this type of charges is given by this parameter Q that is like maybe I should for instance here you can see the Q parameter. So yeah, it's like something that yeah, this is like a fixed parameter. So then the entropy like it grows in a very different way to the ones that you will expect in the zeta space, and then that's like is something that has been like a hotly debated between the people that are working seriously in this type of a topic, whether this is like a good description of the zeta entropy. So to me the answer is simply that this is not the zeta space. That this is like a very different
Right.
type of
It
theory,
cannot
but
be, right. It cannot be.
yeah, exactly. It cannot be the zeta, but it only gives you like some
So
approximate motion.
perhaps it's a geometry related.
Mhm. Sorry.
There is something called Nariai black hole.
Sure,
I'm not sure
sure.
you've heard that, which is I think that has some entropy and it has some charge essentially. No? So there it will make at least sense to compare this entropy you're seeing with that. But the zeta2 is like sort of a vacuum. You don't have any charge there to compare this entropy with.
Correct. Yeah, so all that we are like making the
You understand
comparison is about the like these thermodynamic quantities, even though that they're like different theories. Even from the start, you can see that. But at least in terms of how this hyperfast growth of different observables appears, they seem to correlate in a very nice way, even though that they're like very different. And for instance, you can see, for instance, that this is like a fine UV complete model that this energy in the entropies basically go to a fixed
No,
value
no,
when
I
you
don't
approach.
necessarily. Even if it's a black hole, it's an asymptotically a zeta black hole, which is actually already very interesting. And then you can sort of, perhaps there is a, well, hopefully there is
Okay, a very match in between this. Okay, yeah, I will say that okay, to make the connection even with the zeta in 3D is already like something to the one of this one-dimensional quantum system is something that has been debated in doing it for higher dimensional cases where you have like a true black holes, then it's a bit more complicated. But it will be something nice to develop in the future, probably.
Thank you very much.
Okay, thank you.
Okay. Is there any final comment or question? Well, if we don't have more questions, let us thank Sergio for a very nice talk.
Okay, thank you.